Okay, hello everyone. I'm very glad to welcome all of you to the restart of our international online seminar on interval methods and control engineering. And in fact, we have to celebrate something like our second birthday for this seminar. We are now starting the third year of our international online seminar, in fact, with the 42nd presentation in the seminar series. And yes, I would say at the beginning when we started the seminar series, I didn't expect that it will last for almost 3 years now, but I'm very glad that we still have a huge attendance. Also, we have already scheduled the presentations for the next couple of weeks. And from that point of view, I think without further ado, I'll give over the microphone to you, Genua, and you'll be the session chair today.
Okay, thank you, Andres. Now let's begin our seminar. First, I'd like to introduce today's speaker, Ms. Marit Lahme. Marit Lahme received her Master of Science degree in mechatronics from the Technische Universität Ilmenau, Germany in 2018. She is now a doctoral candidate within the group Distributed Control in Interconnected Systems at the Ossietzky Universität, Oldenburg, Germany. Her research interests include modeling of dynamic systems as well as state and parameter estimation. The title of her presentation is Set-Valued and Statistic Approaches for the Online Identification of the Open Circuit Voltage of Lithium-Ion batteries. Please start your talk, Marit. Thank you.
Yeah, thank you for the introduction. Today I would like to talk about how the open circuit voltage of lithium-ion batteries can be identified using a set-valued approach and a stochastic approach. I will start this presentation with the modeling of lithium-ion batteries using equivalent circuit models. I will then present the set-valued identification approach first, including the state space representation, the design of the interval observer, and the identification approach itself. Afterwards, I will present the stochastic UKF-based identification approach, again, including the state space representation, some preliminaries, and the identification approach itself. I will end this presentation with a conclusion and an outlook on ongoing and future work. So equivalent circuit models like this can be used for approximating the charging or discharging dynamics of lithium-ion batteries. Those models consist of a finite number of RC subnetworks, as well as series resistances and a state of charge-dependent voltage source that represents the open circuit voltage. In this case, we have restricted ourselves to one series resistance and two RC subnetworks that represent processes with short and large time constants. These are, for example, processes like diffusion phenomena or some other chemical reactions. The terminal current IT is used as the input, and the terminal voltage VT can be measured. The system parameters of this model can be identified experimentally, but they are subject to aging and temperature-induced variations that lead, for example, to an increasing ohmic Salz resistance, changes in the charging or discharging efficiency, as well as changes in the time constants or a loss of the total capacity of the battery. All of those variations can be mapped onto the open circuit voltage, and therefore a direct identification of the nonlinear dependency of the open circuit voltage on the state of charge will consider these variations. The state of charge, as well as the voltages across the RC subnetworks, are chosen as the state variables, so that we get the state vector x, where the state of charge is represented by sigma. We also obtain the quasi-linear continuous time state space model as shown on this slide, with the terminal current IT as the input. For the system matrix A, we get the reciprocals of the time constants as entries on the main diagonal, and the input matrix B consists of the reciprocals of the capacities. Both matrices are dependent on the state of charge. Let's have a look on the state equations. The first equation represents the integrating behavior between the state of charge and the terminal current with respect to the capacity of the battery. Here, the state of charge is a normalized value. That means sigma equals 0 represents the completely discharged battery, and sigma equals 1 represents the fully charged battery with the capacitance CBAT. The second and third state equations represent the derivatives of the voltages across the RC subnetworks with the SOC dependent parameters shown here on the right. By applying Kirchhoff's voltage law, we obtain this equation at the top for the terminal voltage. So VT that we can measure equals VOC minus VTS minus VTL minus IT times RS. And the series resistance RS and the open circuit voltage are represented here with nonlinear expressions. The parameters of the open circuit voltage can also be experimentally identified. For the open circuit voltage, we can obtain a quasi-linear representation by subtracting the state-independent terms, in this case V0 and V2, from the expression for the VOC. We then get the expression VOC tilde equals eta times sigma, and eta depends on the state of charge itself. We will use this quasi-linear representation in the output equation. For this output equation, we can also obtain a quasi-linear representation. Therefore, we have to get rid of this term on the right side of the equation. So we just add it to this equation, and we are left with an equation y star that is only dependent on the output matrix C and the state vector x. The output matrix C has the entries eta, -1 and -1. So in other words, we can model our battery system with equivalent circuit models. The prerequisite for our approach is that the system parameters, not yet subject to aging or other variations, are identified beforehand experimentally. We want to obtain the nonlinear dependency of the open circuit voltage on the state of charge, and therefore use the terminal current as an input to charge or discharge the battery. We then measure the terminal voltage VT and obtain a value y star from this measurement that corresponds to the quasi-linear output equation. And in order to calculate the VOC from this equation, we need to know the state variables, but we cannot measure them directly, so we have to estimate them. For this, we design an interval state observer that gives us an estimate x hat with lower and upper bounds for the state vector x that will always contain the real value. The design of this observer is shown in this slide. So from our actual system, we obtain a measurement y that corresponds to the terminal voltage. And we calculate a value y star from this according to this equation at the top. The measurement uncertainty is then considered by the value delta y star m that is either added to or subtracted to this value. The interval observer itself consists of two observers, one that estimates the lower bound and one that estimates the upper bound of our state vector x. Therefore, the weighted sum between the lower or upper bound of the measurement and the lower or upper bound of the estimation is added to the system equations. Both observers use the experimentally identified parameters to model the system. And the observer gain matrix H, as shown on the bottom part of the slide, is designed based on the design of a robust interval observer that can be done, for example, by using LMIs. It is then assigned in the form shown here. The first element has to be greater than 0, and the other elements have to be equal to 0. With this, and with the sign pattern of our system matrix A, the observability is guaranteed. So our interval observers gives us an estimate of the lower and upper bounds of our estimated state vector and our estimated value y star. With our quasi-linear output equation, we can now calculate estimated values with lower and upper bounds for our open circuit voltage and for the state of charge. Now let's have a look on the identification algorithm. From our interval observer, we obtain bounded estimates for the open circuit voltage and the state of charge. These values are depicted as intervals in this chart. And while charging or discharging the battery, we will get or obtain several intervals along this curve. And these intervals will overlap. So by intersecting these intervals, we are able to obtain an approximation for this nonlinear dependency. This chart shows how we intersect these intervals. So let's say that the green interval on the bottom left represents the first measurement, and the yellow interval on the top right represents the second measurement. The intersection between those intervals is represented by the blue area. And we can now assume that this blue area most likely contains the real values for the open circuit voltage and the state of charge. So we cut off the intervals above and below this intersection. We are now left with 3 intervals on the left and on the right, the remaining original intervals, and in the middle, the intersection itself. This process is done every time a new measurement is available, and it is done with all intersecting intervals until no intersections are left between all of them. In order to get good estimation results with our interval observer, we need to have a small discretization step size. That means that we are intersecting a huge number of intervals that are located very close to each other, which leads to a very slow process. As an example, 10 consecutive intervals are shown on the left. What we can do here to speed up this process a little bit is to approximate a certain number of consecutive intervals with the hull over all these intervals, and then only intersect these hulls with one another. This is shown here on the right. The 2 blue intervals are approximated by the hull shown in yellow. A consequence of this is that this approximation will be a little bit more conservative. Now let's talk about some results. This shows the effect of the intersection process. The observer output is shown in yellow and the estimate is shown in blue. We see that after this process, the intervals get smaller and there are no intersections between these intervals. We now add the true value for the VOC. We see that we get a good approximation of the true value. Here, we initialized our open circuit voltage with a linear approximation shown in yellow with lower and upper bounds. And the idea here is that the intersection process will correct this initialization so that we get a better approximation. When we now add here the true value for the VOC, we see that the falsely assumed initialization is corrected and we get a good approximation of our true value. So for the moment, this is what I wanted to say about the set valued approach. Now let's talk about the stochastic approach. For this UKF-based approach, the equivalent circuit model is extended with another variable Z that represents a disturbance voltage. This comprises all effects that are not explicitly represented by the assumed open circuit voltage or the voltage drop across the series resistance RS. These deviations can appear, for example, because of a coarse approximation of the open circuit voltage, because an imprecisely known series resistance, or because of temperature-dependent voltage variations, for example. To estimate this disturbance voltage, the state vector is augmented according to the equation at the bottom left. And in addition, an integrator disturbance model is assumed. With this augmented state vector, we obtain this augmented state space model. If the VOC is identified perfectly, the disturbance voltage Z will be estimated approximately nearly to 0. By applying Kirchhoff's voltage law to the augmented system, we obtain this equation at the bottom. This is just the equation that we saw for the set-valued approach, but with the disturbance voltage Z as an additive element. A prerequisite for this approach is that the whole state vector can be estimated. That means that the system, the augmented system, has to be observable. This can be checked, for example, by using this observability mapping Q, by checking if the associated Jacobian with respect to X has full rank for all values for the VOC. This check holds true for all functions of the VOC that actually depend on the state of charge. This means that already the linear approximation of the open circuit voltage is observable. We will later use this linear approximation as an initialization for the open circuit voltage. And for the implementation of this identification routine, the continuous time system is discretized with a constant step size t and with the help of the explicit Euler method. In the simulation, we used a step size of 10 milliseconds. So how do we deal with other uncertainties? Model mismatches and disturbances that are not accounted for by the disturbance voltage Z are assumed to be normally distributed with zero mean. We consider two additional uncertainties, the process noise and the measurement noise. the process noise is represented by the vector W and parameterized by the covariance matrix CW, which expresses up to 10% uncertainty of the corresponding state variation rates. The measurement noise is represented by the vector V and parameterized by the variance CV, which is set to 0.01. The idea of this identification routine is that an a priori knowledge for the open circuit voltage is corrected based on a classical state and disturbance estimation. We assume that the open circuit voltage is described in a piecewise polynomial form, and therefore we use Bernstein polynomials. Those polynomials form a basis for the polynomials of the order m. And with this, the open circuit voltage can be expressed with a coefficient vector eta multiplied with the vector of the Bernstein polynomials. Additionally, the state of charge is divided into several intervals denoted by the variable n sigma, but the state of charge will remain in an interval between 0 and 1 in total. The Bernstein polynomials are defined by the equation you can see here at the bottom. And what are we doing in our identification routine is to estimate the coefficient vectors eta in each interval to correct the a priori knowledge for the VOC. This is an example for the Bernstein polynomials of the order 3. This is visualized for just one interval, so n sigma equals 1. For the order 3, we get 4 polynomials, and these polynomials always sum up to 1 for each value for the SOC. The open circuit voltage can now be expressed as the sum of these intervals, each multiplied with a coefficient. And what we can see here in this picture is that at the start of the interval and at the end of this interval, the value of the open circuit voltage will only depend on the first or the last coefficient respectively, because all other polynomials are 0 at these times. So this is always the case for Bernstein polynomials, and we can take advantage of this property for defining interface conditions between neighboring intervals. Because to ensure that the approximation is continuously differentiable, we have to consider at least 2 interface conditions. At first, the value of the open circuit voltage at the end of an interval has to be equal to the value at the start of the next interval. And the same holds true for the first derivative. As I said earlier, the value of the open circuit voltage at the start at the interval and the end of the interval will only depends on the first and last coefficient. And for the first derivative, we can see this in this picture as well, will only depend at the start on the first 2 polynomials and at the end on the last 2 polynomials. When we now translate these interface conditions into equality constraints for our coefficients, we see that we can eliminate some of these coefficients. This is shown here on the right. The coefficients that we can eliminate are the eta j plus 1, 0 and eta j plus 1, 1. So for each interval, we can eliminate 2 coefficients, but not for the first one. So we only have to estimate a reduced coefficient vector, which is denoted by n tilde, eta tilde. Like a classical Kalman filter, the UKF also consists of an alternating evaluation of prediction and innovation steps. During those steps, we have to create sigma points to be able to obtain the predicted values. To calculate those sigma points, we add increment vectors, here denoted by x tilde, to the most recent expected value vector, here denoted by x bar. The increment vectors are based on the covariance matrix describing the distribution of the vector x. Or more precisely, the increment vectors are the ith row of the matrix square root of this scaled covariance matrix. Each time, 2 times n sigma points are created, and n is the order of the system. 1/2 of the sigma points is created by adding positive increment vectors, and the other half is created by adding negative increment vectors. So now let's have a look on the identification routine. The stage 1 is a classical state and disturbance estimation. And we start in the prediction step with the most recent expected value for the state vector x and the corresponding coefficient covariance matrix. Based on these values, we compute our first sigma points and propagate them individually through the temporally discretized state equations. We then obtain predictions of those sigma points. With the help of these predicted sigma points, we can then obtain a new mean and a new covariance matrix for the predicted state vector. Based on those predicted values, we compute new sigma points and propagate them individually through the measurement model to get predicted output values. With the help of these predicted outputs, we then are able to obtain associated approximations for the expected value and the covariance matrix. With this covariance matrix and the covariance matrix of the predicted state vector, we are then able to calculate the filter gain and subsequently update our predicted values with respect to the measurement. These estimated values are then saved as an initialization for the next time step, and afterwards we can move on to stage 2. In the stage 2, the identification or correction of the open circuit voltage is performed. From our estimates that we determined in stage 1, we obtain most recent estimates of the coefficient vector eta by first defining an augmented state vector containing the reduced coefficient vector eta tilde and the most recent expected value of the state of charge. The corresponding covariance matrix is created similar to this. The prediction step then corresponds to a forgetting factor technique as it would be done in a classical least squares estimation. With the forgetting factor gamma, we are able to obtain a new mean and a new covariance matrix for the predicted coefficient vector eta. And now the procedure is similar to the innovation step of the stage 1. From these predicted values, we compute sigma points and propagate them individually through the polynomial output model. We then obtain predictions of the VOC. Based on these predictions, we are then able to again obtain associated approximations for the expected values and covariance matrix. Based on this covariance matrix and the covariance matrix of the predicted coefficient vector, we are then again able to calculate the filter gain and update our predicted values with respect to a virtual measurement vector. This virtual measurement vector is calculated from the estimates that we determined in stage 1. These estimates are then again saved as an initialization for the next time step. And for this next time step, we will return to stage 1. As an example, I would like to show how we calculate the predicted values for the state vector and the corresponding covariance matrix. For the predicted values of the state vector, we just calculate the mean over all sigma points. And to obtain the corresponding covariance matrix, we calculate the mean over the squared errors and add the process noise covariance matrix to it. The innovation step of stage 1 or stage 2 also, it corresponds to a innovation step of a classical Kalman filter that is adapted to this identification routine. The prediction step for the stage 2 is a little bit different. As I said earlier, this corresponds to a forgetting factor technique. The forgetting factor gamma is chosen from an interval between 0.95 and 1, and it influences the covariance matrix. To implement the innovation step in the stage 2, we first have to define an augmented state vector that contains the reduced coefficient vector eta tilde and the most recent expected value for the state of charge. In addition, we have to define the virtual measurement vector, which contains the open circuit voltage based on Kirchhoff's voltage law and the state of charge. Now, let's have a look on some results. We investigated 3 cases. Case 1 is a state estimation with a standard UKF, but without a disturbance model. Case 2 is a state estimation with a standard UKF and with a disturbance model. And case 3 is this proposed UKF-based identification routine. For all 3 cases, the initialization for the VOC was set to a linear approximation. The initial conditions were set to identical values, and the input is given as a periodically sinusoidal current. So here we see the estimation error of the state of charge. We see in case 1 that we get a large estimation error, and we cannot really use this approach for applications like SOC equalization in battery management systems. We see that in cases 2 and 3, we get a significant improvement of this estimation error. Here, the estimate of Z is shown for the cases 2 and 3. In case 2, we can see that the periodically input current results in a periodic repeated error estimate. And this can be improved in case 3 by mapping the information of Z onto the coefficients of the open circuit voltage, which results in a reduction of the maximum amplitude of Z in each current period. So in other words, a better identification of the open circuit voltage will result in a reduction of the amplitude of Z. And that means that that is an indicator for the estimation accuracy. Here, the identification results are shown. The open circuit voltage was identified in an interval of the state of charge between approximately 0.4 and 0.9. And already after the first few input periods, the 3 sigma bounds are estimated so that the true value for the open circuit voltage is included over the whole interval. So in this presentation, I showed the derivation of 2 approaches to identify the nonlinear dependency of the open circuit voltage on the state of charge. For the set-valued identification, we intersect estimated intervals for the open circuit voltage and the state of charge that we obtain from an interval observer. To optimize this algorithm, we approximate a certain number of intervals by the hull over all of these intervals. For the stochastic approach, we first perform a classical state and disturbance estimation and use this information afterwards to correct an a priori knowledge for the open circuit voltage. The 2 stages of this approach are based on a UKF. What is also important to notice is that for the set-valued algorithm, the open circuit voltage has to be a time invariant function of the SOC. And for the stochastic approach, the VOC may also be a time varying function of the state of charge. This is because of the forgetting factor gamma. So the results that I showed you today in this presentation are based on simulation results for the measurement data. We are currently working on the verification of these algorithms with measurement data from real battery systems. And of course, there is room for optimization. And an idea to further optimize the set-valued algorithm is to merge all the hulls after a certain time and inflate them to further reduce the number of intervals by maintaining the accuracy of the process. Further work will also be extending these approaches to characteristics that depend on multiple variables. And we will investigate a possible combination of set-valued and stochastic approaches. So for further related publications, please have a look on this list. And then thank you very much for your attention.
Thank you, Marit, for your excellent presentation. Any questions? Any questions from the audience? Please let me ask you the first question. Did you compare your method with some other methods? Some existing methods?
I mean, both of them, or we just compared, or we just compared the 2 processes, but not with other existing methods yet.
You only compare your method with your own methods, but not compare. You did not compare your method with some methods from others, right?
Yes, the case 1 of this slide here is more or less a classical ensemble Kalman filter approach.
You compare your method with some standard UKF method.
Yeah, also that what I showed in this presentation was that we just compared these 3 cases, but not with additional methods.
Okay, I see. Thank you. Any other questions?
Yeah. May I ask something?
Yes, please, Davide.
Okay, so first of all, thanks a lot for the very interesting presentation. So one comment I had is that the open circuit potential is very important when dealing with batteries. So in case this gets identified with significant uncertainty, then it's not going to be very useful, right, for the purpose of estimation and control. So by looking at your results, in my opinion, the uncertainty you get is still too high. Am I wrong on that comment? What is your opinion? Can you comment on that?
I didn't get the first part of the question. Can you please repeat this?
I'll try to say it again. So I think that when dealing with batteries, the open circuit potential is very important. Therefore, in case the uncertainty is too high, then we are in trouble. So I wanted you to comment about the uncertainty you got on the open circuit potential and whether you think it's still too high or not, because I'm afraid probably it's still too high for the purposes of control or anything else. Yeah.
You mean this one? Or so I think we could use it in the control of the battery systems, but I think we can still improve the results.
Yeah, so a comment is, for example, when identifying the open circuit potential, another question I had is, this is usually done by charging the battery and at a very low current. And clearly, by doing so, you can estimate fairly decently the open circuit potential itself. So the question I have, for example, is, why don't you do that, right? And what will be the benefit of this approach rather than, let's say, the traditional method for identifying open circuit potential?
Yes, maybe let me add one point here. The idea here is that we could use the approach as an in situ monitoring approach. That means what you talked about, David, is an approach that you would perform offline. You're once characterizing the open circuit potential, and that's it. The approach that Marit presented is an idea to use it also during the normal operation with arbitrary terminal currents. That's one what one can do. And the other thing is maybe, I think, Marit, if you go back to slide, I think it was 23. No, where you had shown, or maybe 2 slides earlier, where you had shown the covariance matrix and numeric values. Yeah. Yes, the other, yes, this one. Yes, the other comment that David mentioned is the accuracy of the identification of the open circuit potential. This strongly depends on the amount of measurement noise that you have. Yes, and in our case, we assumed a very inaccurate sensor in order to visualize also the mapping of the uncertainty onto the estimated quantities. And there what you can see is this has a standard deviation of 100 millivolts here. And that's a very rough, more or less, even something like a guessing instrument here in order to measure the voltage. And this is the basic reason for the remaining uncertainty.
Yeah, I get these points. I'm just wondering whether, okay, having also the uncertainty on the states will increase somehow the uncertainty you get on the open circuit potential. So while, and I get what you're saying, that it makes totally sense somehow to, let's say, do this also during the online operation, right? So because maybe the open circuit potential is subject to some slight changes over the lifetime of the battery. It's just that I have the feeling while working with batteries that unless this is a very good estimated, then what you can do with the obtained model is not that much. And the last comment I had is about the observability. You mentioned that you assume or that the model is observable. However, I think that I don't know, it strongly depends also on the open circuit potential you have. So I'm not sure whether it's, maybe I did not understand properly, but there are clearly cases where you don't have observability depending on the open circuit potential curve you have. Just to explain it, for example, if the open circuit potential curve appears to be very flat, then it's extremely hard to identify, for example, to observe the state of charge from the voltage.
Okay, yes. Yes, so I think I have to think about this a little bit more, but yes, so we just for the observability, we considered this open circuit voltage that is defined as this, and for this it is observable.
Okay, because it's a simplified case for the open circuit potential curve, right? It's just first order. It's
Yeah, this first order.
Yeah, is it? Because the summation goes up to 1, right? Where you wrote it, right? So the summation was from 0 to 1.
In the other, we considered this one.
Okay. Okay, for example, I've been considering polynomials up to the 7th order, which is usually what is usually done, and then you may lose observability depending on the function you have. That's what I wanted to say.
Okay.
Yes, but Davide, that's a very interesting comment, because what you mentioned is if you're going up to order of 7, you introducing it when you're using monomials of the state of charge. You're introducing also some numerical problems there because your coefficients are scaled extremely poorly, maybe. And what we could do is maybe just as an outlook on some further activities, what we could try to compare is the piecewise polynomial approximation that Marit used. That definitely allows you to reduce the degrees of the polynomials that you're using with this global approximation of a high polynomial order. I think this would be an interesting thing to compare.
Sure, definitely. I will be happy to discuss about it. But just keep in mind, I think my comment is, if you get an open circuit potential that is very flat, then observability is an issue. So in practice, it may happen.
Yeah. Okay. Thank you for that.
Any other questions?
Hello, Marit. First, I will thank you for this presentation, and I have a question about the circuit diagram in the set value part, maybe on page 5.
5. This one.
The circuit diagram. I forgot the page.
The circuit model, or
yes, this page. And I see the current IT is used as the control input, and I want to know in the experiment how to control this variable.
how to control the current as for the input signal?
Yes.
Okay. Yes, we can have a current controller for this, but for this approach, we at first assumed that is not a controlled variable, that we know it exactly. So, but you can use a normal current controller for this.
Do you mean you can control it directly?
Excuse me, I didn't get it. Can you please repeat this, please?
I want to know you control it by control the velocity or control the current directly.
In this case, we didn't control it. We just assumed that we know this input exactly.
Okay.
So
Okay,
this is a knowing input, but not a control input, right?
Okay, I see.
Yeah, so we used this input to charge the battery, but yeah, it has not. You can say it's a control input, but yeah, we used it to charge and discharge the battery to just get the measurements of the terminal voltage.
Okay, I see.
Any other questions from the audience?
Yeah, I would like to raise a question. So Marit, thank you very much for the presentation, and I'm kind of curious too for the input signal. So you developed a simulation, built a simulation setup, and what was the input? Was it the current or the terminal voltage? No, but most likely be the current, right?
Yes, it was the current.
And what kind of time series was it? Was it a constant voltage? Most likely not. Or was it kind of pseudo-random noise, or what was it like?
The current was a periodically current, sinusoidal current, with an amplitude, I think it was 5 amps, and a period of 1 hour.
Okay, so it was a pure, let's say, a sine wave.
Yes.
And do you expect that the results might improve if you switch to another input signal, like random signal or like a rectangular signal, or something like this?
Yeah, I can imagine that this will be different, but I don't really have an expectation for this, so I have to think about it a little bit more. But
what I learned was, if you want to identify something, then you kind of have to shake it.
Robert, you're absolutely right. And there's one thing, it's not related to Marit's presentation today, but I can send you this afterwards. In some previous work, it was concerning the identification of fuel cell systems. What we did, we used Pontryaghin's maximum principle to identify an optimal input sequence. Something that maximizes observability.
Yeah.
This is based somehow on maximizing the observability gradient.
Yeah, and this is something you could use to benchmark your methods. So if you focus on methodologies, then you kind of can set up the perfect experiment. But if you want to apply your approach in real life devices, then you most likely are not free in the choice of the input signal, because your algorithm will only listen to what's happening around, and will not be allowed to charge or discharge the battery heavily.
Yes, and that's again the question concerning the thing that David asked before. If you have the complete freedom to perform an optimal identification experiment, yes, you can do this. You can perform slow charging processes, for example, or you can optimize, like you just said, shake the system however you want. But if you want to perform some in situ monitoring, and then you have to live with the input that is just, yes, the actual system input that results from the application at hand.
Okay, and yeah, I'm on the first page now. I did some screenshots, and I'm on the first page of your UKF based results. Unfortunately, I didn't get the slide number. So there's the depicted the estimation error of the SOC. Yes, this one. Yeah. So this is a rather big estimation error, but this is since the assumed measurement noise in the voltage sensor, right?
Yes, because yeah.
Yes, and the other thing is in the left-hand side, the true open circuit voltage that was simulated was this nonlinear curve, and the estimator had the linear characteristics.
Okay, yeah. So we have the, and we do see the sine wave of the input signal, right? So this is no oscillation introduced by the dynamics of the system, of the modeler, and something like this. So this is the oscillation due to the input signal.
Yes, it highly corresponds to the input signal.
Mm. Okay. Yeah, thank you. Thank you very much, Marit. It was very interesting.
May I ask another question?
Yeah, of course.
So how do you initialize state of charge and the other states, so the voltages? What is the uncertainty you set on them?
The uncertainty is this in the case 3. These are the
On the states, right?
on the states. Yeah, that's the state of charge. And these are the voltages across the RC subnetworks, VTS, VTL, and this is the disturbance voltage.
I see. But so here I think the question I have is how can we make them realistic? So you assume that you know exactly the state of charge. Does it make sense? And do really these uncertainties on the voltages make sense as they are? I'm not criticizing, but this is, I think, a problem, right? In general for this kind of application. And if I can ask another question, sorry about it, but this is more philosophical. We know that the equivalent circuit models are, let's say, not matching 100% the behavior of a battery. So the question I have there, but I don't have the answer, is about the structural uncertainty. So how can we quantify, let's say, the process uncertainty that needs to be added in order really to be consistent with data, because we know that this model is not going to be exact.
No, this model is not 100% exact, but if at first we have to just assume the noise that we put on it, just yeah, from experience, but with this approach, also the model is not exact, but with this approach we can improve the model because we have our disturbance estimation. So when we map this onto our model, we can improve our model.
Yeah, I get totally. So under this assumption on the sigma, and assuming that the model is as it is, so that the structure is correct, then clearly you're gonna reduce your uncertainty. But as I said, it was more a philosophical, let's say, comment. That is to say, in practice, we know that this has some issues, right? Because the model is not, even the structure itself is not gonna be good enough. Because there are electrochemical models that better model and so on. It's more like a comment. I don't expect you to have the right answer. While on the uncertainties on the voltage and so on, so on the states, I wonder whether that is reasonable. So maybe where did you get those values? Why do you think those are reasonable? I think maybe one should think more. Maybe, yeah, I need to think more as well. What values are meaningful in this case? Also because you're assuming that you know exactly the state of charge.
Yeah.
Please go ahead, Marit.
So in this case, yeah, we at the start assumed that we perfectly know the state of, or not perfectly know, but yeah, we know where the state of charge is. And yeah, I think maybe you have to think more about the uncertainties.
Okay, thank you.
Is the thing that I wanted to add to the philosophical question is that what one could try is you could some virtual input to each of the state equations and perform something like an unknown input observer. And then what you could do is for estimating for each of the individual state equations some yes, model mismatch. That's maybe something one could try, but I'm definitely not sure if this remains observable or not.
Yeah, indeed. And besides, I'm not sure whether the number of states you have are enough, right, to match the real behavior, because you're assuming that there is just something missing, but let's say 3 state equations are enough, right?
Yeah. Yes, and the other question is what you just mentioned, if three-state equations are enough or not, also raises the question, for example, concerning long-time delay processes. And that's, for example, something one could also model maybe in a better way using some fractional dynamics. Lower order fractional dynamics may even be more efficient than higher order integer order dynamics. And then it's getting really difficult because, for example, the fractional differentiation order operators, they have to be initialized in an appropriate manner again. And this raises some further questions, some further philosophical and also numerical questions.
Yeah. I mean, the topic is very interesting. So, and I liked a lot the presentation. It's just that I think there are several difficulties and several issues with this application, but the structural uncertainty is a common problem, right, in modeling. So, yeah.
Okay, I think no one else is unmuted. And if there's no one else who has any questions, then yes, I thank Genua for chairing the session. I thank Marit for giving the presentation. I thank all of the audience for participating in the restart of our seminar series. And the remaining thing I would like to wish you is have a nice Friday afternoon, weekend. And yes, I'm hoping to see all of you again on Friday in 2 weeks, where our next speaker will be Rashid Malti from the University of Bordeaux.